Hi and welcome to a new lesson from Easy Chemistry. This is Mr. Kusai, and today, as I promised you, we're going to study the hybridization and the hybrid orbitals as a part of the VSEPR model theory and the geometry of the molecules. Our objectives for today are to explain the hybridization of some atoms, as well as to predict the hybridization of the central atom in a molecule. Before we start the hybridization, I just want guys to go back to the previous video because we have a mistake. We did a mistake there. So this is the correction from the previous video. It was about this example, the BrCl2. Actually, the compound, it was BeCl2. And Be, from the periodic table, it has atomic number of 4. That means the electron configuration is 2 and 2, or 1s2, 2s2. That means we have 4 valence electrons in 2s, and I'm going to write the electron dot structure or the Lewis structure for the Be, which has 2 valence electrons only. And then we have 2 chlorine atoms. Each one has 7 valence electrons because it has 17 electrons. When we do the electron configuration, you will find that it has 7 valence electrons. Same thing for the second chlorine atom. And then we have single bond and single bond between the beryllium with each chlorine atom. That is, the central atom is A, and we have 2 shared pairs and 0 lone pair. That means here we don't have any lone pair, we have 2 shared pairs, so it's going to be 2 shared and 0 lone. That means we need 2 hybrid orbitals, sp, so it's going to be the hybridization is sp, and the shape of this molecule is bent. So that was the correction from the previous video. I'm going actually to add this correction to that video so we don't do any mistakes in our videos. Now, let's start with the hybridization. What is meant by hybridization? Hybridization is mixing of 2 or more atomic orbitals to form a new set of hybrid orbitals. We will understand the definition when we do the examples. And it has some rules. The first, mix at least 2 non-equivalent atomic orbitals, for example, s and p, s, p, and d, etc. Also, the hybrid orbitals have a very different shape, as you will see, from the original atomic orbitals. Number 2, number of hybrid orbitals is equal to the number of pure atomic orbitals used in the hybridization process. So the number of hybrid orbitals, they equal to the pure atomic orbitals they are used in the hybridization. Number 3, the covalent bonds are formed either by overlap of hybrid orbitals with atomic orbitals or overlap with hybrid orbitals with another hybrid or other hybrid orbitals. Let's check these diagrams. This is the formation of sp. As you can see, we have only s, and we have px. So this is the overlap between s and p. Only one orbital from p, which result into the formation of sp hybrid orbital. Now here, this is the s, and we have 2 orbitals from p, which are px and py. And then when there is an overlap between s and px and py, the result will be sp2, because 2 orbitals from the sublevel b. Here we have also overlap between s and px, py, and pz. That means it's an overlap between s and the 3 orbitals of p results in the formation of sp3 hybrid orbitals. Don't forget, we have here sp, and the original orbitals or atomic orbitals are s and p. Two atomic orbitals, they result in two hybrid orbitals, sp. The result of overlapping s and 2p orbitals is going to give you three hybrid orbitals. And here it will give you four hybrid orbitals. Let's check. The formation of hybrid orbitals. The first example is going to be the formation of sp3. As you can see, this is s orbital, which has a spherical shape. And these are the three p orbitals, px, py, and pz. When they overlap together, they will give you the shape of a tetrahedral. Let's check how this occurs. For example, if we are talking about the carbon atom, which has 6 electrons, and the electron configuration is going to be 1s2, 2s2, 2p6, 2p2. All right, now the valence electrons are 4. If I'm going to write it for the valence electrons, I'm going to write the diagrams for the valence electrons. So it's going to be in 2s, we have 2 electrons, and in 2p, we have 2px, 2py, and 2pz. And we have 2 electrons, one in px and one in py. What happened actually is one electron from s will promote to p. It will be promoted to 2pz. And the result of this promotion is going to give you the hybridization, which is s four new orbitals, hybrid orbitals, and it will give you 4 single electrons, one single electron in each orbital. And this hybridization, because it's between s and the 3 orbitals of p, is going to be sp3. Now, how many sp3 orbitals? How many hybrid orbitals? 1, 2, 3, and 4, because we start from 4 atomic orbitals, which are 2s, 2px, 2py, and 2pz. Don't forget, when we use the VSEPR model theory, we say that for the hybridization sp3, we have 3 geometries. One of them is the tetrahedral. Tetrahedral geometry. And this is the example of the tetrahedral geometry, which has an sp3 hybridization. This is the CH4 molecule. What about the other hybridization, which is the sp2? Now, in the sp2, we have only s overlapping with only 2 orbitals of p, px and py. After combining those atomic orbitals, these are the shapes of the hybridization, the sp2. Let's have an example. For example, if I have the the boron atom, and this molecule is BCl3. Boron, from the periodic table, it has atomic number of 5. So the electron configuration is going to be 1s2, 2s2, and 2p1. Now, the valence electrons are 3, because in the energy level number 2, we have 2 in 2s and 1 in 2p. If I'm going to draw it, it's going to be 2s, we have 2 electrons, and higher energy 2p, we have 2px, 2py, and 2pz, and we have only 1 electron in 2px. Similarly, what will happen is a promotion of the electron from 2s to 2py to give you the hybrid orbitals. Let's check now the hybrid orbitals. This is the hybridization process. It will give you one electron in S, one electron in 2px, and one electron in 2py, leaving 2pz empty as an atomic orbital, not a hybrid orbital. So this is the 2pz, which is empty, and here we have three hybrid orbitals of sp2. Here we have the hybrid orbitals, and here we have the atomic orbital, not hybrid orbitals. So the number of hybrid orbitals are three. The number of hybrid orbitals is 3, 1, 2, 3, because the overlapping was between one atomic orbital, which is 2s, and two atomic orbitals, 2px and 2py. So the total number is a 3. Last example for today about the hybridization is the sp. And sp is the simplest one because only one orbital from s and one orbital from p, which is px in this case. And this is the result of the hybridization. We forgot here to just mention the geometry of the shape. We already know that sp2, because we have three bondings, shared pairs, zero lone pair, so the total pairs is 3, so it's going to be trigonal planar. In this case now, we have only S with only P, and if we take this example, which is BeCl2, Be, the atomic number is 4, so it's going to be 1s2 and 2s2. What happened is 2s, we have 2 electrons, but also we have 2p, which is empty, no electrons, 2px, 2py, and 2pz, empty. Also, there is a promotion of this electron to the 2px, and what happened is the hybridization will become like this. Only two hybrid orbitals because it's between only one s and one p orbital, atomic orbital. So it's going to be one electron and one electron, two hybrid orbitals, and leaving 2py, 2pz as atomic orbitals, but they are empty. So these two are atomic orbitals, not hybrid orbitals. And here we have two hybrid orbitals. And then the hybridization is going to be sp. If we use the VSEPR model theory, you will find that for the beryllium, we have two shared pairs, zero lone pair, and then the total pairs is 2. Hybrid orbitals are sp only because we need 2 bonds, and then the geometry of the molecule is linear. These are the three hybridization that we need to study today. We're going to continue about the hybridization maybe next video, but let's check our understanding about this practice problem. Determine the hybridization state of the central atom in each of the following molecules. The first one, we're going to check Al(I3), aluminum iodide. Al, from the periodic table, it has atomic number of 13. The electron configuration is going to be 1s2, 2s2, 2p6, 3s2, and 3p1. These are the valence electrons. So I'm going to write it in 3s. I have 2 electrons. Sorry about my handwriting. And then in 3px, 3py, and 3pz, we have only one electron in P. So what happened is one electron from 3s will promote to 3py, give you the hybridization, which is going to be three hybrid orbitals, s, p, and p. So it's going to be three hybrid orbitals. They also have the exactly same energy with single bond each, and the hybridization will be s, p, and p. So it's going to be sp2, leaving 3pz as atomic orbital, and it's empty. Now we need to check according to the VSEPR model theory. The Al, it has a three valence electrons, and it's bonded to three iodine atoms. The number of shared pairs is 3. The number of lone pairs is 0. The total pairs is 3. Hybridization should be spp, so sp2, and then the geometry will be trigonal planar. Just like what we saw it in this example here. This is the one, or BCl3, ALI3, trigonal planar. And this is the sp2. See how it's trigonal planar? All right. The second example in this problem, PF3. So in B, we have PF3, and P from the periodic table, it has atomic number of 15. So it's going to be 1s2, 2s2, 2p6, 3s2, and 3p3 in this case. Now, the valence electrons are 5. This is 3. 3s2 and 3p10 3. So 3s, it has 2 electrons, and in a 3p we have also 3 electrons. Here, no need to do any promotion for this electron because they will overlap together and they will give you this hybrid orbitals. 4 hybrid orbitals because the hybridization is between s and the 3p. So s, p, p, p. 3 p's, so 4 hybrid orbitals. The first one has 2 electrons, the second one has 1, third has 1, and the fourth has 1. Now we have 3 fluorine atoms. Each one needs 1 electron, so they will share with these 3 electrons. Let's check now. Phosphorus, it has 5 valence electrons, so 1, 2, 3, 4, and 5 valence electrons. We have 3 fluorine atoms, and they will do 3 shared pairs, so the number of shared pairs equals to 3, and the number of lone pairs equals also to 3. Sorry, the number of lone pairs equals to 1 lone pair. So the total pairs are 4. One of them is lone pair. So the hybridization should be sp3 as we found it here. So it's going to be sp3 right there. And the geometry should be trigonal pyramidal. I want you guys to have an example problem to solve it by yourself, which is, let's say, C, PF5. at this time. What is the hybrid orbitals? What is the geometry of this molecule? And try to do it, and then we're going to solve it next video, in the beginning of the next video. What we need to take from this video: what is hybridization? It's a mixing of two or more atomic orbitals to form new hybrid orbitals. We have some rules. The most important thing is the number of hybrid orbitals equal to the number of atomic orbitals used in the hybridization process. And then the covalent bonds, it's formed between overlapping hybrid orbitals with atomic orbitals, or hybrid orbitals with other hybrid orbitals. In next video, we're going to check the hybridization, or the different types of hybridization of the carbon atoms depending on the molecule it's in. I hope you guys learned something new. If you have any question, just write it in the comments. I will read all the comments and I will answer all your questions. Have a nice day.